some community, and I started a series of social events and lectures, and we called ourselves the Women Math Warriors. So now you know the secret symbol as well. And by the way, we welcome, you know, we welcome people of any gender, whatever, into our community. And more, I'm going to give some more advertisements later. Okay, so I'm actually going to talk about stochastic difference equations. So that's okay. It's a little different than differential equations, so it's going to be kind of fun. But a difference equation can also model something changing. Today's talk is going to be a little more abstract, and it touches on something I've been really interested in since my Ph.D. days, which is this intersection between deterministic rules and randomness. You know, how do those things sort of play out together? So a difference equation is just something that describes that it's a function that gives you the state of a variable at the next time step, as opposed to a continuous evolution. And for example, to tie it into yesterday's talk a little bit, suppose we have a variable x that maybe measures the quantity of something, happiness, population, whatever, and the law of evolution is f of x, the state at the next time step is just some constant times x. Okay, so like you have a bunny, you have 2 bunnies, looking familiar, 4 bunnies, 8 bunnies, 16 bunnies, and so that, as we saw yesterday, the solution to that is what? X 2 to the t. So if we index our iterations, we call them by t, then we'll the tth iterate will be x0 times 2 to the t. Okay, so that's exponential growth. And the way we graph these, so since I thought I'd show you something you're familiar with, we take the graph, lambda times x, or f of x, we graph it on top of on the same axes as a diagonal, and then to iterate, to see what happens if we apply this law over and over again, we start with x, we find f of x, we have to then switch the vertical and horizontal coordinates, so that's where we use the diagonal. We go horizontally to the diagonal, vertically to the function, et cetera. And that's how we can sort of graphically figure out what's going on over the long term. So probably some of you have seen this before. So just here's another one that's very famous, the Logistic Map. And we call these self-limiting growth laws because they may describe growth. So lambda times x, but then you multiply it by a term that gets smaller as your population or your state variable gets bigger. And you saw here I graphed the function again on top of the diagonal, and you saw the little red dot represented the iterates of the function, so applying the function over and over. So how many people have seen this kind of picture before? Yay, good. Remember what it's called, what we call it? Rhymes with Bobweb. Cobweb diagram, that's what we call it. It's just a way to graphically analyze the long-term behavior of the system. Because we, as dynamical systems people, that's what we That's what we worry about. So in this first example, our growth parameter lambda was 2.7. Now we're going to make it bigger, 3.7. And I just graphed it again. Notice the parabola is like kind of stretched out more, right? But, and there's the diagonal, here's our initial value, and what's going to happen is it doesn't seem to settle down anymore, right? And that was sort of a big discovery by Robert May back in the day. And so what we care about when we talk about dynamical systems or as chaoticists, we ask the question, do these iterates, does this state variable, these evolution of the state variable settle down to something, or does it not? Does it go crazy like in the last case? And it turns out that this family of functions where we change this parameter lambda has been well studied, And I'm sure some of you have seen that for lower values of lambda, the state variable will always go to a fixed point. So that's going to be a place where the function crosses the diagonal, because then f of x equals x. And so then if you're at that point, the variable won't change. In this case, it settles down to this fixed point. So we say that's a stable fixed point. In this case, it doesn't. All right, so what happens now if we make that parameter? So we saw that it matters what that parameter lambda is. What happens if we make that parameter random and just, you know, pick it randomly? And why would we want to even study that? Well, one reason is that if we are actually trying to describe something, I think it's just cool. But if you're trying to describe something in the real world, we never know exactly what those parameters are, or they may change. They may depend on the environment. For example, if this is a bunny population, maybe one year you get a lot of rain, there's a lot of bunny food, and hence more bunnies. Maybe one year there's a bunch of hawks come and live there, and there are fewer bunnies, right? So that parameter might change randomly because of the environment. Economists are really interested in this type of equation as well, because there's a lot of random factors which might be the environment, but might also be people's behavior is not very predictable. This is, Jennifer mentioned, I wrote a paper with my dad yesterday. This long title had in it the words bounded rationality. And that means you study the behavior of people who aren't always rational, right? So they don't always do the best thing. You know people like that? Yeah. So that's another reason why we might be interested in this unpredictability inherent in life. Okay, so here, what if we just take the simplest sort of exponential, would-be exponential growth, and I say vary this parameter lambda. Now, when lambda's bigger than 1, what happens? What happens is I iterate this function. I apply it over and over again. It grows, because every time I'm multiplying the variable by something bigger than 1, it's going to grow and grow and grow. If lambda's less than 1, then what's going to happen? It's going to shrink to 0. So it really matters whether lambda's bigger than 1 or less than 1. So, and we're going to look at the case where lambda is going to go from bigger than 1 to less than 1, that also we're going to pick it in such a way that its distribution depends on the value of x. Okay, so when x is big, you're more likely to pick a number less than 1, so it'll shrink. When x is small, you're going to be more likely to pick a number bigger than 1, so x will grow. And this is a example of a self-regulating process, a bit like a thermostat on the wall, where you raise it when you're, too cold, but it takes a little while to get up there, and then go down, and et cetera. Okay, so I want to study these processes. Okay, I already talked about that. So here's an example where I'm picking lambda just randomly from a normal distribution, and I'm plotting the same thing. Let me do that again. This graph, I'm just plotting the diagonal. I see this thing just kind of wandering around. It's not settling down. It's not really doing that much. And that's because this growth parameter is normally distributed above and below 1, so with a standard deviation of 0.5. But I wanted to say that we have this feedback, right? So that the growth parameter depends on x. So here's how we're going to set it up. We're going to say our parameter is we're going to pick it uniformly in this interval of width 1. But that interval is going to move up if x is small and down if x is big. And so this is how we write it down. our parameter is going to be uniformly distributed between 1 minus x and 2 minus x. Does that make sense? So if x is close to 0, our parameter is going to be pretty much between 1 and 2. If x is close to 1, that's the biggest it'll be, it'll be between 0 and 1, less than 1 most likely. Make sense? And so we can rewrite this actually in a nicer way so that we take out that dependence on x in the distribution by just picking a uniform number between 0 and 1, which kind of is nicer, add 1 and subtract x, and then multiply by x, because this is our growth parameter. Okay, so this is the system I want to study. Make sense so far? All right, now let's just look at these functions for various values of the parameter. They all look like these parabolas. It's not quite like the logistic map, but similar. They all go through 0. And as I make lambda larger, I pick a larger, these graphs get steeper. Here's the diagonal. And they all cross the diagonal exactly twice, once at 0, and then once again farther up, except for when lambda is exactly equal to 0. It only crosses once at 0. So they have 2 fixed points because they cross the diagonal twice. And it turns out it's easy to show that in all cases, the one that where it crosses, and it turns out it crosses exactly at lambda, the value lambda, that's kind of why we picked this, makes it nice, is stable, which means that no matter where we start, unless we start exactly at 0, the functions, the iterates, will converge to that stable fixed point. And now, what were we going to do? Remember? I know it's early, but remember what we were going to do? We were going to pick lambda randomly. So imagine each year or whatever generation, day, or whatever this time represents, we're going to randomly pick one of these parabolas. So each time, it's the x variable is going to want to go towards the value of lambda you picked. But then you're going to pick another one. It'll go towards that one. So this is what it looks like. I think if I click, it'll go. Nope. Sometimes it does. Sometimes it doesn't. So that's what it looks like. Here I drew the average lambda value, which is when lambda is 1/2. And it just kind of wanders about, right, that average fixed point. So how can we actually study these things? Well, so now I'm going to get a little more techno, but I think that's fun. It's one of the funnest things about math. You get to use this cool notation. Only math and music you use like cool notation, right? Maybe dance, they have some. And so remember in the deterministic case, all the x values would go towards that value of lambda, whatever it was, if it were fixed. Now, how can we describe the behavior, the long-term behavior of the system? So instead of looking at the values of x, we're going to look at distributions of x. And for that, so we're going to say the distribution of x values, what's the likelihood of them being here or there, evolves with time. And the way it evolves is described by this operator, which is just a function of a function. In this case, a function of a distribution or a density, and we call it the Perron-Frobenius operator. That's just named after 2 guys. Some people call it the Frobenius-Perron operator. I don't know which is right. Doesn't matter. So here is how we describe it. Suppose we have a density f. Now here, f is now not our function anymore. If you notice, I switched to t. Before, f is now our distribution, and the operator is called p, and it takes a distribution f, here, our original one, to p of f. And it does it by integrating for each y value, and there's a picture here, I'll show you, y against the probability of, the g is the probability of picking a particular lambda, so the lambda densities. So here's the picture, like for a particular x value, and in this area, it's weird, we draw x on the vertical axis. Just as tradition, so go with me, it's kind of fun to twist your head around. X on the vertical axis, y on the horizontal axis. So for a particular x value, we're going to say, what's the new density at x? Well, so think of it sort of as the probability of arriving at x. Well, how could you arrive at x? You could pick a y and a lambda pair that gives you x. So here, this graph, this yellow region, is sort of all the possible parabola graphs from all the different lambda values, from lambda equals 0 at the bottom to lambda equals 1 at the top. And so let's say, how could I get this particular x value? I could pick this y value and this biggest lambda value, lambda equals 1, or this y value and this lambda value, the one that goes through here, or this y value and this, right? And so the probability of arriving at this x is the probability of picking all those y lambda pairs that make you land at that height. Does that make sense? So that's all that integral means. And then we want to ask, well, what happens if we apply this over and over? So here's a picture of what happens. If I start with a uniform density of x's, so I just randomly pick x values, equally likely any x value, and I apply this function once to each of those x values, I get a new distribution of x's. That's what that operator does. And it turns that uniform distribution into something that looks like this. This is just a simulation after one iteration of this function. So it says that no matter if you start uniformly distributed between 0 and 1, after one time step, you're more likely to be around a quarter. You're less likely to be at 0, and you're less likely, really less likely to be way up at 1. So does the kind of picture make sense? And so we can do this over and over, just like we looked at the x values marching around. We can look at these densities evolving. And we can also write down what that operator does as a formula if we know what the distribution of lambdas are. So if we say we're equally likely to pick any parameter value between 0 and 1, so anywhere in this yellow thing, then I can actually write down what that operator is by doing some calculus and algebra, and I get this nice formula. And I can actually take the functions and then apply this formula over and over instead of just simulating it in R or whatever. And then instead of looking for stable fixed points, stable values of x, we can say, do those densities stabilize anywhere? And so we have some words, so we call that an invariant density if we have a density that doesn't change under this operator P, so under iterating. And if no matter what density we start with, we converge to that density, we call that density asymptotically stable. Whoops, asymptotically stable. So now we've switched our universes from just looking at stable fixed points to stable densities, which is all we can do because we're in a randomly changing world now, okay? So in our case of the uniform distribution, I showed you that formula. We can iterate that formula. So we start with a uniform distribution of x's. And now I've plotted the first, third, 9th, 12th, 15th, 18th, and 50th iteration. And you can see that the densities, at least they look like they're converging, right? To this thing, this density that's very small at 0, jumps up at a quarter and kind of curves off to 0 at 1. My students call this the shark fin distribution. It doesn't have another name like the normal distribution. So we'll call it the shark fin distribution. And I've shown this to other people. They go, wow, we saw this same distribution come up in these various things you do on the internet and everything. So I think it's not that weird, but we're still like discovering where these things appear. All right, so that's like showing you numerically that this thing converges. And I'm just going to really briefly, just to give you a flavor of what you'd have to do to actually prove that there's an invariant stable density. Because I don't know, you guys who raised your hand said you'd seen those cobwebs before. Do you remember how you prove that a fixed point is stable? How do you do it, someone? Look at the absolute value of the derivative at that point, and if it's less than 1 in the discrete case, then it's stable. If it's bigger than 1, then things are spreading out, and it's unstable. So in this case, we have to do, it's a little more work, but it's similar. We write, instead of the derivative, we write our operator with this, here's our original density, f. We write it as the integral of this kernel, which you can actually write out what it is in terms of the lambda distribution, whatever, this kernel. And then if you can show, this is a lot of words, but just so you can iterate this kernel, right, over and over and over. If you can show that the kernel, eventually, this is the mth iterate, is positive sort of everywhere. So in other words, if this density is sort of smeared out everywhere, which is this purple thing I've drawn in the simulation, then you can show that P is asymptotically stable. Sort of makes sense in that, if no matter where you start, what x values, where they are, if they're sort of getting smeared all over, then everything will look kind of the same. It won't matter where you start, and we'll maybe end up with some uniform thing. So that's the idea. And there's a little bit of technical stuff in there, but just not that complicated. Okay, so we can show that in this case, it's asymptotically stable. So then we know that there's this invariant density, that's a shark fin density. It's stable no matter where you start. You'll converge to that density, so you're more likely to have values at a quarter, et cetera. The question now is, now we know there's a density, so we can ask stuff like, what is the average? What's the expected value? So this question can be interpreted in sort of in terms of the original process as follows. Suppose I have a population, and I have this, it's changing according to this law. And let's say the law has lambda being a half. And now so you have, it converges to a half. We know that. Now let's say I take that lambda value of the parameter and just start wiggling it, adding noise. Am I going to reduce the average or increase the average or just leave it the same? That's the question. I have an average value, half. If I just do that lambda value, it always converges to a half. Half a half. If I wiggle the lambda, will it increase on average or decrease? What do you guys think? We have one increase. Anyone else? Stay the same? Stay the same. Anyone else? Okay, so I'm just writing this down for my mathematical great-great-nephew. The Gothic Theorem tells us that actually this makes sense once we have this invariant density. It just says the average, if I average along the x values, that's going to be the same as the expected value, integrating against the density. So it kind of makes sense. All right, so it turns out, we asked, does this noise make the average bigger or smaller or stay the same? Turns out, it makes it smaller. Weird. Huh. And it's not that hard to prove, so I'm going to show you. And actually, this paper here I wrote down is another example of it. So turns out this is sort of a common thing, that adding noise with certain types of functions actually hurts the population. Or if x is your happiness, it hurts your happiness. So here's the proof. I'll just show you because it's pretty easy. although it has some, so by the ergodic theorem, we can say the average value along the iterates, if we average all the x values, just like taking this integral, just the same as taking this integral. F star is our invariant shark fin density. I write out what that nice formula was, then do some manipulation. So see how it's a double integral, right? Because I write F star as this integral, because it's invariant, so F star is equal to P of F star. Then I switch the order of integration. Remember doing that? It's really fun. And you get this, and you can integrate some of it out. And then, now this integral is pretty simple, and remember that the integral from 0 to 1 of y, f of y, is just the average value. So this becomes 3/2 times the average value. This becomes -1 times the expected value of x squared, because we have y times y, right? Then we use Jensen's inequality that says that the expected value of x squared is bigger than the expected value of x squared. And then we just remember that we started with the expected value of x, rearrange, and you get that this expression has to be positive. The expected value of x is positive, so we know that 1 minus 2 times the expected value of x is positive, rearrange. And the expected value of x is less than 1/2, which was the expected value of the deterministic case, right? When we use the average parameter. So how much different? Well, here I actually simulated this process and for 10,000 iterates, and then did it a whole bunch of times. And I got this distribution. So the average of these averages is about 0.44 something. So it went down. I don't know if that's a lot or not. Depends what you're talking about. Make sense so far? Question? Okay, so I'm going to pose a few challenges in today's talk so that you guys can have something to think about on your drives home. The first challenge is, I gave you this formula for this Perron-Frobenius operator, and I said, we know that there exists this function, f, that's invariant under this operator. In other words, I put in this shark fin function for f, and I do all this junk, and I get out the same f. So the challenge is find that function, the formula for that function. I showed you a picture of it. Looks like a shark fin. I can prove some things about it, which is that it's not differentiable at a quarter. You know, it goes up to a point. I can prove that it goes to 0 at both ends, but I don't know the formula for it. So if you want to figure that out, that'd be cool. The best I tried, but the story goes that von Neumann just guessed the invariant density for a similar deal with the logistic family. So I thought, von Neumann, I'll try it, just guessing. So I just guessed, because I have the graph of it, you know, looks maybe arcs, and also it's got these integrals with, if you do change of variable, these 1 minus root 1 minus x, you know, kind of like arc signs and things. Okay, tried stuff. So this is my best guess. 83 over 32x arctan of this junk. And here's I don't know if you can see very well, this red one, here's this guessed one, that's my best guess. And the blue one is the invariant density that I numerically computed. So they're not exactly the same, but they're pretty close. So that's my challenge to you, your first challenge. Figure out what that formula is. And it's just a matter of, you know, you could just guess and then try plugging it in. So for each x value, you know, you just plug in these limits. The x value gives you these limits, and you try to make them equal. Okay, fun, huh? Alrighty, now other distributions. So that was when I picked a uniform distribution of lambdas. We can look at other distributions. Here's a uniform, a normal distribution. But always, no matter what distribution you pick, that theorem didn't depend on the distribution. You get that the average is smaller. Well, that's because this asymptotic stability and that average argument just depend on the lambda distribution. and the fact that we have stable fixed points for every lambda value, and the loss of capacity, I call that that the average gets smaller, just depends on the convexity of those maps. So really this result should apply to any family of functions that has stable fixed points for each lambda value, and then has that convex shape. So then there are other questions, of course, that arise. So here are some other distributions. If you take discrete distributions, so now I'm just going to pick between two lambda values, 7/8 and 1/4, and we get this kind of, this is the invariant distribution. It looks like a, so instead of a shark fin, it looks like this Cantor set thing. It's kind of cool. Haven't been able to prove that yet, but notice the average value is, again, less than the average lambda value. Other families of maps, here's the logistic map. Like I said, you can prove the same result because the convexity is the same. They all have stable fixed points as long as you're in the right parameter range. So what about, but what about maps that don't have these stable fixed points? So this is a student of mine, Maricela, who graduated a year ago. She's now a graduate student at UC Irvine. And she looked at parameter values for the logistic map in this period 2 regime. So those of you who are familiar with this, if you increase lambda in the logistic map up above 3, you get this alternating. You don't have a stable fixed point anymore. They alternate between two things. So what happens then? Well, first, here's this bifurcation diagram that probably some of you have seen for the logistic map. If we start varying lambda randomly, we get a new looking bifurcation diagram, right? Because it's going to fuzz out a bit. In fact, it looks kind of like a kiwi bird. You know, do you see how it's fuzz? So here's the period 2 regime, kind of where this eye is. And so Maricela looked at whether the average was now also smaller, like it was in the case we looked at before, when you added the randomness. And it turns out that actually, so here you get these you get a density, evolution of densities. So here she's showing the evolution evolving. And you get this sort of 2-humped density. So it makes sense because it used to be period 2. But then if you look at the average, and this is all done numerically, they look pretty close. Here's the average of, if you use the average lambda value versus the average x values when you change lambda. But if you zoom in, you can see that actually now the average value along the average x value is now larger when we added the noise. It's switched. Remember before it was smaller, now it's larger. Why? Because we don't have stable fixed points anymore. We have stable period 2 orbits. Huh. Who would have thought? Is there a reason for this? Well, oh, sorry, I jumped ahead because I don't want to run out of time. So it's here, we proved that in the period 1 regime, when we had a stable fixed point, the noise hurts, right? The average got lower. We can prove that. Maricela conjectures, just by her numerical experiments, that the noise in the period 2 regime actually helps. She also went into the period, maybe some of you know, that then you increase lambda further, you get into a period 4 regime. Again, numerically, it seems to hurt, et cetera. And that's just what she found by numerically trying things. So your next challenge is to, prove this. Prove that, we've proved number 1, but we haven't proved 2, 3, or the et cetera, okay? So here, yeah.
So is the et cetera, it helps again, that hurts?
Yeah, that it'll flip as you keep period doubling, as you keep moving along that parameter. So
chaos?
So when you get to chaos, who knows? So there actually is an example where if you let the parameters go into the chaotic regime, and sort of span the whole thing from stable fixed points to chaotic regime, you no longer have an invariant density. So that's another issue. But in these regimes, you do, because when you do the iterates, you still have stability. So one thought that we had to prove, say, number 2, is to use a technique that from renormalization, which is the following. So I just want to give you a hint of this. So if I look at the second iterate of the logistic map, which I wrote down up here. So here's the logistic map, lambda x 1 minus x. Now we do lambda times that, because we're doing another iterate. Lambda times, this is our new x, times 1 minus lambda x 1 minus x, okay? So it's a 4th degree polynomial. We can graph it. Here it is for a particular parameter value. So we have these fixed points, 1, 2, 3. These 2 new fixed points are the period 2 points. So, and they're stable. Under the second iterate, there's stable fixed points because it's a second iterate. If I take this graph and just look at the middle part and kind of turn it upside down, right? And zoom in, ha! It looks like the original map, the first iterate. And that's renormalization. That's how they actually proved that this Feigenbaum's constant is what it is, right? It's sort of a rescaling and a flipping. And so maybe, because notice, this looks like the original, but I flipped it upside down. So the convexity, here it's concave down, but actually it was concave up. So maybe that's why it flips back and forth. Maybe. I'm leaving that to you guys to prove. Work out the details. Okay. That's your challenge. Let's see what time it is. So now back to the shark fin family. Modeling self-limiting growth. So here, I actually started looking at this problem because of a colleague suggested that this type of self-limiting growth might be, with this randomness, might be a model for some kind of disease like cancer taking over, or, so you have this population that's kind of randomly varying. If it ever gets above a certain threshold, something bad happens. Or maybe you're modeling a population, and if it gets below a certain threshold, it goes extinct or something. So I originally wanted to show what the distribution of times until crossing a threshold would look like. And that's when I started studying this. So extinction or maybe epidemics. If sometimes, this is a red tide, picture of red tide. So if a population gets above a certain critical threshold, maybe it's bad. If it gets below a certain threshold, it's bad. So, so in this case, we're gonna have this randomly changing shark fin family, and if the x value gets, say, above something, then it's gonna crash. And I made a little, instead of looking at graphs, we can listen to this. Made a little, uh-oh. Oh, dear. Oh, no, I can't see it. I should have tried this. I don't know how to make this smaller. Oh, there. Okay, see if this works. So what I'm going to do is start the system off, and I can change this death threshold. Right now it's at 0.99. So it's going to go along, and I can change the range of lambda values. So here, actually, this is a different version where lambda went, I hadn't subtracted 1, so it goes from 0 to 2 instead of -1 to 1. So same function, I just rewrote it. So here we go. Let's see if I can, oh no, I did it. Sorry, how did I do that? Okay, let's see if this works. So I started off. The values there. threshold. Lower. Yeah, it's randomly going around. Gets to above 0.9, it's going to crash. Kind of pretty, huh? Maybe I better make it 0.8 so it'll crash. Okay, let's try it again, just for fun. Just up here. Oh, it crashed right away. Let's try it again. Down there. Variety. So you see, sometimes it takes a long time, sometimes it takes a short time, because it's random. So the question is, if I did it a whole bunch of times, what's the distribution of those times until crashing? Make sense what the question is? And people believed, for a variety of reasons, that if you plotted that distribution, it would obey this power law. So here's a graphical thing. So here's the x values, they go up and down, and now I'm looking at the threshold. I plotted the threshold at a quarter, and I'm looking at these times between crossings. Why did people believe that it would be a -3/2 power law? Well, they just see that all the time in nature. So my original goal was to prove that, and but then I realized there were all sorts of issues, like I didn't even know if this was well defined and everything, but I did do some numerical simulations, and it does, here's a bunch of, did a whole bunch of times, plotted the log of how long it took before it crashed against how often that time occurred, and plotted it on a log-log plot, and the slope is -1.3. So not minus 1.5 as they thought, but pretty close, right? Pretty close. So why might it be -1.5? Well, if you had just Brownian motion, just a random walk, you would get -1.5 as the slope of this log-log graph. So there are, I have some ideas how to attack that. Now we know there's this invariant density, but haven't done that yet, so there's another challenge for you. That's the third one. And I kind of like this idea of, so here's our graph of all the possible maps, and sort of thinking of it as a Markov chain where I pick some lambdas and other lambdas, and if I get up here, this interval of x values gets stretched, right? If I have an x value close to 1, actually at the next iterate, I could have pretty much any x value. So this interval of x values gets stretched across the entire interval. These intervals don't, they stay small. So I think of this as a horseshoe. So those of you who've had some dynamical systems theory, the horseshoe is when you get chaotic behavior. And I think of this as a stochastic horseshoe, and that's why I think that it will look like a random walk, independent random walk, because we could show that you have actually very close to independent behavior. Okay, so finally, I want to show you what I really wanted to prove, which is not just look at one of these systems. I wanted to actually think of this as a whole piece, as a whole spatial collection of little areas where things were growing and keeping and stabilizing, and maybe a piece of tissue, and the thing keeping it under control was your immune response, right? And but the cells there were trying to escape and grow. And so you have this sort of negative global feedback. Positive local feedback means locally the cells were trying to promote growth. And so we can model this by a sort of growth, stochastic growth law on a lattice. Oh, wait a minute. where each place on the lattice has one of these maps going on, and then it's coupled to its neighbors. So I have the growth law at location ij, looks just like what we had, but instead of having lambda, or lambda plus 1 minus x, it's lambda minus the average x value over the whole region. So you think of I think of the host as noticing, whoa, this whole population of cells is getting out of control, I got to keep it down, right? And then the local positive feedback would be if this x value is big, its neighbors are going to, in the next iterate, or if its neighbors are big, this population is going to be more likely to be large. And we know that tumors do this. They change their environment by making it more acidic. That will increase the ability of new cancer cells to grow. So that's the connection between my work I was talking about yesterday. So I want to show you some simulations of that super quick. So here's where there's no help from the neighbors. So I started with a random set of x values on this grid and let this run. So here the coupling term, epsilon, is 0. So we're just looking at the host trying to keep this system down. Now you can remember that crashing thing or the threshold thing. You can imagine if the population gets above a threshold, that would be bad. But here you can see the red ones are the hot spots, but they're kind of kept isolated and under control. But we might want to know, this probability of getting over a certain threshold, how long that might take. Here's where we increase that coupling a little bit to 0.101. So now the neighbors are helping, and you can see that again, we have hot spots, but now they're a little larger. This says that if the neighbors can help, even with everything else being the same, you're more likely to get these clumps. And here is when we increase that coupling even more. Again, overall, the average isn't changing, but these clumps of high populations get bigger, which makes sense, right? So, so what we're interested in is now finding formulas to predict how long before the whole entire population gets above a threshold based on these things. So that's a sort of more theoretical approach. Here's just the stills of the last bit. So here's no coupling, or no, it's very small coupling. You have sort of two isolated clumps. Larger coupling, nothing else different. You can really get this spreading of things. So that would be the final challenge, is to really figure out how these couplings determine the distribution of times to cross those dangerous thresholds. And we can simulate it, and we get something, again, pretty close. This is now the slope. The best fit slope was minus 1.5. Of course, in honesty, I'll tell you that this was the best one I got, right? But I think that there's something here. I think it'll work out. There's another one. Okay, so in summary, we showed that this stochastic self-regulating one-dimensional thing was ergodic, meaning it had a well-defined average, and that the population was lowered by the addition of noise, that you seem to find this everywhere in all sorts of families of functions. In the stable period 2 regime, you seem to, it flips. The overall dynamics seems to look like a horseshoe. The crossing times seem to obey a minus Fiat's power law, and lattice coupling gives this hot spots that grow as that coupling constant increases. So I'm going to just advertise a little bit, a few programs, because I feel like I want people to know about these things. We're all about, why did you come here on your weekend and drive through the snow? Well, it's not really snowy. Because we believe we're creating a community. So I wanted to tell you about a few things that I'm involved in. Jennifer said I'm now director of this program and president of the nonprofit that we started to support this program called EDGE program. here's the URL to go find it. It supports women. Any of you who know women or who are women going to graduate school, check it out. It's a great program. We'll be in DC this summer. It moves around every summer. We have some edgers now who are at the University of Minnesota, so maybe I'll try to get them to come over here or next year. The Association for Women in Mathematics. Anyone can join. We have actually 14% men as our membership are men. It's a national organization. It's big, and here's my student Aisha getting a picture taken with the past president. She won a prize or something. Here's the URL. You can, if you have a student chapter at your school, everybody gets free memberships. It's not very expensive, and they do a lot of things that support student activities that can help you network, help your careers, all sorts of kinds of mathematicians. And so I wanted to tell you about that. And then finally, I was in a movie called The Empowerment Project. This is a documentary that these two filmmakers made, that their goal was to reach out to everybody, but their target was sort of younger women, to show them that you can do anything you want, if you're not afraid to fail. So they went around the country interviewing all sorts of women, and congressmen, and pilots, generals, and Miss America, and me. and for this, the reason why I'm showing you this weekend only, up till tomorrow, you can go onto indieflix.com and stream it for free. Usually they charge money. It's sort of IndieFlix is like Netflix for documentaries. So for the next few years, you won't be able to buy it or rent it or anything unless you do a big showing. But you can watch it for free this weekend. So there you go. Thanks very, very much to the organizers. This is a really great event, and I know it takes a lot of work to put these on. Thanks to you guys for listening.
Thank you, Amy. Questions? We have a few minutes before the student talks begin, so.
Yeah.
With the shark fin function you showed, I think on the picture it's at 50 iterations. Is that really, do you think it's close to the limit, or?
Yeah, I think, yeah. So you're talking about, backwards in time. Yeah, you can see even that after, the 15th, which is this one, you don't really see any change. So yeah, I think that's pretty close.
So it's not limiting to like a step on the other side of it?
No, it never, right. It's always smooth. In fact, you can show that it's differentiable, just take right by, you can show it's differentiable except at a quarter. And you can.
Because the uniform distribution is not differentiable, is that what causes that?
It has to do with this picture. So imagine raising this x value up. At first, each x value has two preimages, two pieces. And then when you get to a quarter, you're right here. And so that you have one piece, and it's like a huge change. So that's why. Yeah. So, and if you want any of these challenges written down so you can work on them, I could give you the slides.
Well, I have a question.
Yes.
So in terms of applying this, as you suggested, we might talk about tumor growth, but all of this depends on, you've made assumptions about the original density and so on. Is this going to be more personalized medicine? Is choices going to come from, well, where are they going to come from? From molecular?
Yeah.
Genetics, or piles of microarray data, or? how are we going to get a handle on
Right.
actually putting this kind of theory to work?
So I think this sort of exploration is much more qualitative, and we're not trying to say, oh, tumor cells actually behave this way. We're trying to like get a qualitative idea of what might describe very macroscopic sort of survival statistics. So so we won't ever know exactly what first of all, that function, just you're describing the whole population as, that's like crazy, right? But so it's sort of a very phenomenological description. Now, one thing I didn't say is that the guy who proposed this to me to look at with the whole lattice and everything, he'd actually looked at a bunch of survival statistics for different types of cancers and showed that, they were very correlated with certain gross topological features of coupled kind of system. So that was sort of the motivation, was that there was this very macroscopic, big population level data that we're kind of trying to address. This is not about like one person, it's more about, in general, large statistics. Yeah, but yeah, I mean, maybe down the road, you could put some of these ideas in with the more detailed models like I showed you guys yesterday and get more, which are like, you're really measuring specific things, but yeah.
Can you talk a little bit about the choice to use discrete difference equations instead of continuous differential equations? Is that driven more by the phenomenon you're trying to model or by the techniques that are available?
So this is more driven by the kind of phenomenon. So in other words, you can say, what happens next is sort of everything's continually changing and da-da-da. But a lot of things don't act that way. They sort of are on clocks and they change, and you get really different behavior. So you can get very complicated behavior with a one-dimensional system in the discrete world that you can't get in the continuous differential equations world. You have to go up to higher dimensions. So that's why we wanted to look at that. And it sort of simplifies things in a way, but it makes them more complicated in a way. But we thought it made it more complicated in a way that might actually happen. Yeah. But I think it's cool to sort of compare them.
Tumor growth, there is
some clocks, and it seems, could be.
Well-defined time steps?
Yeah, could be. Don't know. And then, but that's an excellent question. You're really good. You guys are good at asking questions. Do we get similar things in the continuous case? I don't know. Haven't looked at that. Yeah, that's a good question. Challenge 4, 5. What are we at? Any other questions?